Today is the last day of lecture. So what's today, April 26th? So what happens after today? So your midterm is due May 10th, which is a Wednesday. So between now and May 8th, during our regular lecture time, I will be in my office having office hours, and you can come and ask me any term paper questions that you have. If the demand for those office hours turns out to be too large, then we'll figure out some way to get everyone's term paper questions answered. Are there any questions about that? I think that was the only announcement that I wanted to make. So, okay, if not, then let's go ahead and jump into the lecture. So, we're going to start with a definition, and y'all asked some questions last time that sort of like led into this definition. So let's let E be an extension field of F. And we'll let f of x be a polynomial with coefficients from f. Then we'll say that f splits in E. If it can be factored as a product of linear factors in E. Okay, and then we'll call E a splitting field for F if basically that's the smallest such field that accomplishes this. So E is a splitting field for F. For this polynomial f of x, if F splits in E, but it does not split in any proper subfield of E. Okay, are there any questions about the definition? So we'll do some examples. Oh, and let me just write down some notation as well. So, if F is a field and A1 up to AN are elements of an extension, then F parentheses A1 up to AN is the smallest subfield of E containing both F and all of those elements. Okay, are there questions about that part? Okay, so let's do some examples of splitting and splitting fields. So the polynomial x squared plus 1 in Qx. What's a field where this splits? Yeah. Yeah, so this splits in C. Is C a splitting field for this polynomial? No. Yeah, so, okay, so I saw people shaking their heads. So it's not a splitting field. What is a splitting field? Hey, Bean? He's like extra crazy today. Yeah.
Like the field of complex numbers with rational parts.
Complex numbers with what?
With rational parts.
Yeah, so the splitting field for it would be like in the notation that we just introduced, Qi. So this would be like A plus Bi, where A and B are from Q. Okay, good. Are there questions about that example? So then like kind of another example along similar lines would be x squared minus 2 over Q. Right, so square root of 2 does not live in Q, so this would split in R. But we can make a smaller field where it splits, so the splitting field would be Q parentheses root 2. And you can show that this is equal to, similarly, A plus B root 2, where A and B are Q's. Okay, are there any questions about those definitions or the examples? So we're going to prove two theorems. The first one that we're going to prove just shows the existence of splitting fields. And then the second one will tell you how to write the fields that we've been looking at, so like fx mod px, as something like this. Okay, so let's prove the existence of splitting fields. So let's let f be a field. And f of x be a non-constant element of fx. Then the statement will be that there exists a splitting field for f of x over f. So there exists a splitting field for f of x over f, which just means that the splitting field will be a field extension of f. Okay, so for the proof, we're going to go by induction on the degree of f. So what should the base case be? Yeah. Yeah, so if the degree of f is 1, then f is just linear. So it's like ax plus b. In which case, the root of f is already contained in the field, big F. So that means that big F is a splitting field for little f. Okay, are there questions about that part? Yeah.
Not necessarily about this part, but I just wanted to make sure I understand. Is it possible for a polynomial to have multiple different splitting fields, or is there only just one? I mean, with respect to a certain field.
Yeah, so I think if you take the coefficients over like a fixed like initial like ground field, then the splitting field will be unique. And we'll see in the proof of this theorem why it's unique. Yeah.
How are we showing that this is the smallest field? Like no subfield works as well.
Yeah.
How are we showing it?
So we're going to write it. Oh, like
Have you shown it on
I see. So you're saying like why is there no smaller? So since we're taking our polynomial to have coefficients in f, the splitting field for it will automatically be in some extension of f. Because it's just like it's like where did we start, basically. Yeah. So for example, like if you took this polynomial and you thought of it as a polynomial with coefficients in Cx, then C is a splitting field. Yeah. Okay, other questions? Okay, then let's do the inductive step. So for that, we'll suppose that the statement holds for all fields and all polynomials of degree less than f. Okay, so last time we showed that there is some extension E of f in which the polynomial f will have a root. Right, so from last time, there exists an extension E of f in which f has a root. Let's call it A1. Okay, then over E we can write f of x is equal to x minus A1 times g of x for some g of x in EX. And then since the degree of g is smaller than the degree of f, by induction, there's a field, so by induction, there is a field K, which is an extension of E, containing all of the roots of G. And let's call those roots a2 up to an. Okay, then what is the smallest field in which f splits? Well, we need all of the roots of f, definitely, to be in that field. And the smallest field containing f and all of those roots is going to be this one, just by definition. So this field is the smallest subfield of K containing f and the roots of f of x. So this is a splitting field for f. Okay, and that finishes the proof. So are there questions about this? Yeah.
And I get like the argument, but what exactly is this small subset? How is it constructed? What is it?
Yeah, I think at this moment it's not that clear. Today we won't get to like results that make it clear, but basically, like in short, you can show that there exists an element such that this is f of b for some b, and then you need to find the right polynomial for which this is a root. So like a kind of like a minimal irreducible polynomial that has that as a root, and then your field will be like fx mod that polynomial. Yeah. Other questions? Okay, so let's do the second theorem. So this theorem says, what are these fields fx mod px that we've been looking at? What are these isomorphic to? So let's let f be a field, and we'll let px in fx be irreducible over f. Or sorry, that should be a big F. Okay, then if there's some element A, which is a 0 of px in some extension E of f, then the field f parentheses A, which I usually I pronounce this f adjoin A. So f adjoin A is isomorphic to the field fx mod the ideal generated by px. So maybe let's just think about what this theorem says in the context of the example that we've been looking at throughout about I. So this says that R adjoin I, which we know is C. So this is Rx mod x squared plus 1. So in the context of the example, maybe it's not that surprising, but like I think the generality of it is useful. So you'll know that like how does this field kind of work? Well, it just is as though we added an element to our field f, which is a root of that polynomial. Okay, are there questions about the statement before we prove it? Okay, so the way that we're going to prove this is through the first isomorphism theorem. So we'll set up a map and then sort of show that the kernel of the map is this px. So for that, let's consider the function phi from polynomials with coefficients in f to the field f adjoint a, given by sending a polynomial f of x to evaluating the polynomial at a. Okay, does the setup make sense? So, okay, so maybe we should just observe that this is a ring homomorphism. So it should preserve the operations, which I think is clear. You know, if you add two polynomials, then clearly evaluating them would be the same as if you did it in reverse, and same for multiplication. So I don't think we need to go any further into that. And then I'm going to claim that the kernel of phi is the ideal generated by px. Okay, so why is that? So we know that P of A was chosen to be a root of the polynomial P, so P of A is equal to 0. So that means that the ideal generated by Px is a subset of the kernel of phi. Do you all agree? Okay, so then we know that this ideal is a maximal ideal because P is irreducible, and we had a theorem that said irreducible gives maximal ideals. So that means that either kernel of phi is equal to this or it's equal to the whole thing. Okay, why can't it be the whole thing? Yeah. Yeah, so like for example, like 1 is a polynomial in here, right? And where does 1 get sent to? Yeah, so 1 is not in the kernel. So since 1 is not in the kernel, we cannot have this case. So that means that we have to have that the kernel of phi is P of x. Okay, so then what does the first isomorphism theorem say? that's going to say that fx mod px is isomorphic to the image of phi, right? So what is the image of phi? I guess we want this to be all of FA, right? Or sorry, we want it to, big FA. So why should it be? Yeah.
Because the file contains or they're like all the constant values of f, x, like the constant values of f. There's also x, which can be a.
Yeah, so, okay, yeah. So the image of phi definitely contains, so it contains the field f as images of the constant polynomials, and it contains the element a as the image of the polynomial x. And then, so now what? Why do we know that it's a field? Maybe that's a silly question because we know that the image of phi, whatever it is isomorphic to this thing, which is a field. So, okay, so this is a field. And it contains these two things, and it doesn't contain anything else, right? Because everything in there is just like taking things from either of these and adding and multiplying them. So it must equal FA. Okay, so then that concludes the proof. Are there questions? Okay, so that was all that I had for the lecture. So now I'll put up the exercises. I changed these a little bit from the ones that are online. So if you want more exercises or like a harder version of this problem, you can look in the files on Canvas. There's one additional problem and then a harder version of problem 7. So yeah, go ahead and split up into groups and work on these problems, and I'll come around and answer any questions as they come up.